So I'd like to thank you all for coming this morning. I know it is very early, especially for those of us who traveled from time zones further west. It's a little unusual to get up this early in the morning, and I thank you for coming. I know that in the past I have occasionally been accused of talking in my sleep. This morning we're going to find out whether I can talk in my sleep and make sense. I hope you don't mind. We're giving you a little bit of a bait and switch this morning. I believe the title in the program book, which was submitted several months ago, said we'd be talking about advanced genotype calling and imputation. We're still going to cover those topics, but we're also going to cover a little bit about next generation sequencing. This is a topic that we've been very interested in at Golden Helix for some time now, and we'd like to talk to you a little bit about how we see that field progressing in regards to our product in particular. Now, I'm just curious to know, before we dive into much, how many of you are either current users or at some point have used the Golden Helix software? Show of hand. So about half, maybe. How many of you consider data analysis your primary function in your job? Maybe under a quarter. Okay. How many of you consider yourselves wet lab scientists? Okay. A few more. Clinicians or just other people in biotechnology industry? Okay. That helps me know how to get going here. So to begin with, we'll talk a little bit about Golden Helix, who we are, what we do, and progress through some discussion of advanced genotype calling, imputation, the strengths and weaknesses of imputation, and get into a discussion of sequence data from there. To begin with, Golden Helix has been around for a little over 12 years now. Our primary business is in selling and producing software for genome-wide association testing, for SNPs, CNVs, and other markers as well. We also have tools available for predictive modeling and diagnostic development, and for analytics services as well. We have a number of strategic partners in both the academic and commercial space. Our primary product is the SNP and Variation Suite version 7. It's a fully functional tool for genetic analysis and associations, for statistical analysis of genetic data, And if you stop by our booth in the exhibit hall later today, you can see live demonstrations for any of the items here. A few things we're especially proud of that are going to be especially relevant as we move into analysis of sequence data are the ability to handle extremely large data sets and the ability to have seamless integration of annotations for virtually any genome you can come up with. So our software tools are in use at a variety of institutions around the world. Some of you might see your own here. I hope you do. And if not, I hope you see it there in the future. We're cited in a number of scholarly articles in a variety of journals. And to tell you a little bit about myself, my position as Director of Services at Golden Helix is in providing consulting analysis work or custom analysis. And so in the past year or so, I've been able to participate in the analysis of 10 or 12 different GWAS data sets. And in addition to that, I also have some responsibilities related to tech support at Golden Helix. So I have had the opportunity to see a lot of data sets produced at a lot of different labs. I've seen a handful of really good projects. I've seen a few that had serious flaws. And in general this morning, I'd just like to share with you some of my experience as I've reviewed a lot of different data sets over the past year. And to frame our discussion this morning, I'd just like to point out, as we all know, the data sets we're working with are growing really fast. The SNP arrays are getting bigger and bigger. Illumina's just put out their 2.5M, the 5M's on the horizon. We are seeing more and more custom arrays being built, but in addition to that, we can't ignore the fact any longer that the sequencing revolution is well underway. We're going to be swamped in sequence data very soon, and we need to be ready to analyze that. And as these data sets get ever bigger, we need to be smarter and more efficient about how we do the analysis. The biggest problem I have seen with these growing data sets is that the type 1 error rates, the false positives, just keep getting to be a bigger and bigger problem. We need to develop methods that control for that problem as much as possible. And largely, it's a matter of data quality and data completeness. I've found that if you can start off with the highest quality data possible, you can really do a lot to limit the number of false positives that you're potentially having to spend a lot of time and money following up on. I don't know, I assume that some of you are familiar with Dr. Robert Elston. He's one of the patron saints of statistical genetics, and I recently heard him really passionately declare this particular point, that any discussion of power is really not relevant unless you speak about it in terms of the type 1 error rates. I can give you a statistic that will find every significant signal perfectly, but it will also come with so many false positives that you'll not know what to do with it all. So as we're looking for more complete and better quality data, one of the big things that we have found in the past year is that if you can improve your genotype calls, you can make a lot of progress. And that's what we're going to start out by talking about, is a program called Beagle Call that we have found to be very useful for improving genotype calls. So there's a big problem in the field, we can't deny it, of spurious associations that are very often, not always, but very often due to experimental problems, either some batch effects or other artifacts creeping into the data as a result of differences in how samples are processed and handled in the lab, or a variety of factors. We won't spend too much time about that right now. But there's sort of this experimental inertia in the field of just dropping SNPs based on a handful of really arbitrary criteria. I don't know if arbitrary is the right word, but if you go back and look, the idea of filtering SNPs on call rates, on Hardy-Weinberg equilibrium scores, and other common filters, it all started several years ago really with the Wellcome Trust papers and others that found we've got all these spurious associations. What do we do with them? Well, it looks like a lot of them have low call rate SNPs. Let's just throw out all the low call rates and see what's left. And we think really it's better if you can get to the source of the problem and either fix the data or at least understand what went wrong rather than just applying a blanket filter and getting rid of it. And of course, dropping SNPs like that may result in losing real signals, and even the strictest filtering won't always get rid of experimental artifacts and other batch effects. And of course, the problem of low call rates, that can affect your power, especially with variants that have lower and lower minor allele frequencies. And also, if you're trying to combine data across multiple studies in a mega-analysis, I know I have found over and over again that there will be experimental differences, other things related to the genotype calling that create inconsistencies that result in all kinds of messy results that you have to sort through. So with that in mind, we've found that Beagle Call has been very good for reducing this experimental noise. Now, what it does is it starts out with some basic or baseline genotype calls. You have to start with calls that are already made in some other algorithm, but it considers both those calls and the LD structure across multiple subjects and references it back against the original allele intensity clusters, and goes through multiple iterations of comparing clustering versus haplotype structure, then back to clustering, back to haplotype structure, until it can come up with the best answer for what the correct genotype should be. So really it's a system of parallel reliability in a lot of ways. There's more ways to call genotypes than just looking at the allele clustering. So as some examples here, if you look on the left side, these are some really pretty nice clusters for making genotype calls. We have across the bottom our allele A clusters, we have our allele B intensity, excuse me, not clusters, and then we have homozygous A's, heterozygotes, homozygous B calls. There are a few scattered points in the middle that are maybe a little ambiguous, but largely you can be pretty confident about 99% of your calls here. This figure on the top is using calls made by Beagle Call, on the bottom by birdseed, so this is Affymetrix data. But on the right, you see a very different example, and this actually comes from a study where some of the samples were blood-based, others were from saliva, and you can see that there's either maybe some performance issues related to the B allele probes or something. They're just not getting really good clarity or separation between the signal, and there's a lot of overlap. Birdseed just colored a band through the middle of here. All of these magenta-colored points were not given a genotype call. But with Beagle Call, it was able to use the haplotype structure to reconstruct what the most likely genotypes were, and with very high probability assign a correct genotype. And you can see that the blue and orange points for the heterozygous calls and the homozygous calls are all mixed together there. But there's evidence that it is very correct, and I'll show you that in just a moment. Here's a different example that is something that I'm still a little dubious about, which is when the minor allele is quite rare. You can see that with this instance, that birdseed had tried to force 3 different genotype classes onto what looks like it should be one cluster here with a very rare minor allele. Beagle Call, I think, corrected that quite nicely, put everything as homozygous for the common allele with a few heterozygote calls up here. There is some question, just due to the fact that with very rare minor alleles, the correlation structure in the haplotypes may not be strong enough to give really good certainty of calls when you're basing it on that LD structure, but in my experience so far it works quite well. The one failure I have seen was an example where a study had been run on 2 different scanners in the same lab, and one of the scanners consistently gave stronger intensity signals, and so there were some markers that were completely monomorphic, but it appeared as 2 separate clusters, and Beagle Call normally corrected that, but there were a few examples where multiple SNPs consecutively were monomorphic like that, and Beagle Call picked up the artifact of the scanner as being some kind of a real haplotype where everybody was consistently homozygous or consistently heterozygous right there, but it was completely due to the scanner, and it ended up resulting in 4 or 6 spurious association signals that we had to go back and clean up. But here's an example that came right out of the original paper describing Beagle Call. Beagle Call was developed by Brian Browning, formerly at Auckland University in New Zealand. He's now at the University of Washington in Seattle. And of course, he also developed the Beagle imputation package. And it's the haplotype capabilities and the phasing capabilities of Beagle that are incorporated into Beagle Call to improve the call. So here is an example using the Chiamo package for genotype calls, and you can see a similar pattern where Chiamo had given a large number of missing genotype calls, where Beagle Call was able to correct that and actually believed that there was some bleed over between the clusters here.